So hey there YouTube, I just finished working, and so now I'm going to come over to my little play area here, which I've just cleaned up. I've added a new shelf. So down here, my doggie's got her little bed and she's all comfy. The next level, I've got my computer, and you see that this is machine number 1 where I can test things that use a parallel port. Over here, I've got my electronics section and the second computer that's set up with a MESA card. And so if you look on top, the first one's got 2 parallel ports. I've got 5 stepper motor drivers, and I've got 5 stepper motors configured as a 5-axis, which is really cool because I can build stuff out of Lego now, make a scale model of something, and experiment on how to make it work. And then over here, I've got the MESA card, and I've got a little breadboard area so that I can set up different things and experiment with them. And I'm going to do a video. People still had questions on how to interface things, so we're going to play with that, possibly a little bit later in this video. And as I said, I've got my other computer here, and it dawned on me that the 2 computers were the same height, so I just laid a piece of cabinet on top of them. Works out really good. And down here I've got this little button, and when I push it, I switch from one computer to the other one. So this is the MESA computer that's over here, and if I click the button again, it'll switch over to this one, which is kind of cool. So that allows me a lot of freedom in what I can do. And this is my good girl. That's Maggie May. And she doesn't know what's going on. You a good girl? You're not even going to look at me? No? You're the good girl. Yes, you are. She's like, leave me alone. You do your thing, I'll do mine. One of my subscribers, Srinivasa, has the MESA 5i25 card. And for some reason, it's not coming up. So we had some emails going back and forth, and it looked like there was a single power supply. And so I had sent some more information back and forth, and we determined that there's a 72-volt power supply to drive the stepper motors and a 24-volt supply for the MESA card itself. So after looking at that and getting a little bit more information, I want to kind of proceed and try to give an assist on getting this thing working. You were saying that you were not able to detect the 5i25 card, and this could also apply to a 6i25 card. Internally, they're very similar. Anyway, if you're not detecting it, there's a couple of things that could be going on. Inside the 5i25 or 6i25 board, there's a couple of jumpers. They need to be set to tell it to supply 5 volts to the exterior board. And I'm not going to open this up and everything. I've got one of my MESA videos already covers that. But to refresh on the MESA card, the external card, there's one of the jumpers here and one of the jumpers is here. Both of those have to be in the forward position. They have to be this way. All right, and that tells it that this is going to supply the 5 volts for this to operate. The other thing that you have to be aware of is that you need to have your either 12 or 24 volt power supply. I personally like 24 volt power supply, but it's your personal preference. That has to be turned on and supplying voltage up here to the positive here and the ground here. If not, inside of here is a serial chip. And if that serial chip doesn't get voltage, what will happen is your Linux CNC is going to start to power up, and it's not going to detect the entire board. And it's going to give you one of those errors, and it's going to fault out and say, hey, I can't find the board. So you've got to make sure that your power supply is turned on before you run the Linux CNC. If you do that, it should come up and it should detect it normally. If not, you've got something else going on and you'll have to take a look at your connections. Peter Anderson asked me if I had done a follow-up video on the features property in the INI file. No, I haven't. Let me explain briefly what the features is. So if you open up any INI file, this is the FrankenLab INI file, for example, and we scroll down until we get to this RS274NGC section, you'll see that usually in here there's a path for your variables, and then I add a path here for the subroutines, and then there's always this little features 12. The features 12 gives it some extra things. It allows it to pass variables from a G code down into Linux CNC and some other things. Now the number 12 can be changed, but I'm telling you, for 99% of anything we're ever going to do, just leave it as 12. Wayne Baker was talking about the opto isolators, and I had used them in one of my Mesa videos, and he was having a little bit trouble still understanding exactly how they worked, so I sent him the link to the Mesa video, and this is it right there. And I told him if he needed more help to let him know, and he said, yeah, I'd love it if you could make a video on that. So let's go ahead and do that, and we'll cover a little bit more about the optocouplers. All right. One of the questions that I get a lot is, how do you connect different voltages together? In other words, let's say that I've got a Raspberry Pi or I've got an Arduino, and it outputs a signal that's 3.3 volts, give or take, or even 5 volts. And you want to connect it up to this, which is currently set to use 24 volts. Obviously, you can't just connect the two of them together. You're going to blow something. So how do you do that? Or say that you've got this and you want to take the output and you want it to drive something that's 5 volts or 3.3 volts. Again, how do you do it without damaging it? Well, there's something called an opto isolator, and I did a bunch of fancy graphics, but I'm just going to do it the down and dirty way. And what that is it consists of basically an LED like that. All right? Then it's got a photodetector like that, and they're encapsulated in plastic. So what happens is when this LED shines light on here, it conducts. Okay? It's fairly simple. So what you need to do is you need to take whatever voltage you're going to run, and you need to put the appropriate resistor here so that you don't damage it. That turns this on, which then turns this on. And I won't say that the 4N35 is my favorite and that I order a lot, but yeah, I do. I order these things by the 25 tube. It's my favorite interface. And we'll go through and I'll set up a little experiment on the lab and kind of give you an idea how you do it. Okay, so as you can see, I've got the Mesa cards set up here. This is going back to the computer. These are the step generators, 1, 2, 3, 4, and 5. This is some other connections we're not going to get into right now. 5 volt power, and these over here for spindle control. All right. So, and this orange one is our 24 volt supply, plus and minus. So over here and over here, we've got a bunch of inputs and outputs. So everything from here to here is inputs 1 through 16. This is input 17 through 32. And these are outputs 1 through 8 and then 9 through 16. So what we're going to be doing is we're going to be experimenting with input number 1 for now and output number 1. And so for the input, we're going to actually go and look at it and set it up with Linux CNC so that we have a little red light and we can see what's going on. And then this one I'm going to wire up and set it to be mist coolant because it's something that I can very easily turn on and off. So the first thing that we're going to do is we're going to take this yellow wire right here and we're going to insert it into input number 1, and I'm going to tighten this down. So now we've got the input set up, and for the moment I'm going to just plug it into a random point right here. So what that means is that now I can sit there and I can either take a positive signal and connect it, or I can take a negative signal and connect it and look at what the reactions are to the device. So to do this, I'm going to fire up the computer here, and so you see we've got our 5-volt indication. Now I'm going to plug in the power supply, and you see now we've got our indication for 24 volts. So this rail is a 5-volt rail. This is 24 volts, and as you can see I've got 5 volts attached to these rails. So I can pick which kind of voltage I want to play with here in my experiment. So let me go ahead and fire up Linux CNC and we'll set up an input. Alright, I know this isn't the best thing filming off a screen, but it'll be enough to prove what we're trying to do here. So I'm going to open up the lab. Alright, and so the lab is connected to the Mesa card. And I was corrected on this. It's Mesa, not Mesa. Mesa as in table from Spanish, from American Indian and so forth. So Mesa card, okay? So anyway, we come in here and we're going to go and look at the HAL configuration. And I am going to look at pins, signals. And you see that there's a digital in. I've programmed that to be input number 1 on the card. So if I click on watch and I add this pin, we can see what the reactions are live. Okay, so I've got this connected up, and we are going to first try connecting 24 volts to that input. And look at that. We get a change. Alright? Which means that this device needs to be driven by having the pin pulled high. So I'm going to move this over here to the button now and plug this into here. And if I click on this button, oh wait, there's an issue there. What is going on? So the connections have to be made on the same side as the button. That's an unusual button. But anyway, we've proven it. And in fact, I'm going to use green to signify power on this, just so I don't get messed up here. That this is 24 volts. And actually, I think I'm going to go on the other side of the button so I'm not tripping over it for the rest of the experiment here. Let's test that out. Yay, that works. So to trip this thing, we have to pull it up to 24 volts. So we'll make a note of that so that later on when we're going to try doing it with a smaller voltage, we know what we've got to do. Alright, so now I want to connect an output. So 8, 7, 6, 5, 4, 3, 2, 1 would be this one right here. So what I need to do is connect that wire to the input. So now I've got a couple of LEDs over here, and I am going to take this and plug it into the high side, and I'm going to take this, a ground, and plug it into the low side through a resistor. And we can see that it is not illuminated. So now what I want to try to do is I want to go over here and I want to hit the mist coolant on. And I clicked it on and I clicked it off, on and off, and you see I'm not seeing any change, which tells me that either I've got it wired backwards or this doesn't take that kind of an output. So the first thing I'm going to do is I'm going to rewire it. I need a little bit longer cable here. Yeah, I got a black one. So I'll take the black cable and put it to the resistor. Put this on this side. Let's try it. Nothing. All right. Now I'll reverse these connections. And I'll try it. Nothing's happening. So now let's try this. What happens if I put in 24 volts? Will this supply a ground? Let's try that. Ah, it does. So you can see the way this works now. So what happens is 24 volts comes into our device, and this supplies a ground when activated. So those are two important concepts. Now that we've got that, we can figure out how to make an interface for it. This is connecting the Mesa output, which is 24 volts, to control a lower voltage, in this case 3.3 volts. Now I'm going to show you how to do a device, and for the test device in the lab we'll just use an LED, and I'm also going to show you how to connect up an Arduino pin. Or it could be a Raspberry Pi, any microprocessor or whatever that uses a 3.3 volt input, or basically something you wouldn't want to shove 24 volts into. So we're going to be talking about an opto isolator, and the heart of the opto isolator is this little LED. And the LED is basically a diode. When you run voltage through it, it lights up. Then there's a photodetector, all right? And we take these and we encapsulate it into a piece of plastic. So the light can shine from the LED to the photodetector and be detected, but all the outside light is blocked. So it's a really good device. Now there's also some internal wires that connect stuff up, and then there's some pins that come out of the device that allow us to connect up to it. So we're going to have 3.3 volts. We're going to have some device that you want to turn on. We'll say an LED in this case. And we're going to have ground. Now we know we're going to connect the 3.3 volts up to the device, and then we're going to turn it on by connecting a ground to it. So first we need to connect up 24 volts to the opto isolator's input. And then what we need to do is on pin 2, we need to connect our output port. Now, if you recall from the lab we just did, the output port sits there and floats about 24 volts or so, so no current is flowing through the little LED. Then when it drops down to ground, when it's activated, it completes the circuit and voltage will flow through the LED. Now we're going to take our device and we're going to connect it up to pin 5, and we're going to connect our ground up to pin 4. So when the photodiode is operational, the 3.3 volts should go through whatever our device is, through pin 5, through the opto isolator, and out pin 4 to ground, and it should turn on. And once it's lit up, we've got the current flow. That's pretty simple. But now let's look at some problems that we have. We don't know how much resistance, how many ohms to put between that 24 volts and that pin 1, because 24 volts is probably way too much for that little device. So we're going to need a resistor in there. Now we know we've got 24 volts. So you go to Bing or go to Google or whatever your favorite search engine is, you look up the data sheet for a 4N35, which is the opto I'm going to use, and you find out that that little internal LED runs on 1.2 volts. Well, it doesn't take a lot of math to figure out that we're 22.8 volts too high. All right, way too much voltage for this little thing. So we also look in the data sheet, and it's going to tell us how much current should be flowing through there. And I want you to think of it like a stream. Basically, we need the equivalent of your garden hose, not some 50-foot wide stream running through there. So we need to reduce it down, and that's what a resistor does. It resists the flow. So it says that it runs at 10 milliamps. So milli means that we take the decimal place, move it 3 points, and we've got 0.010 amps. So you can see that's a very small number. So then we take the amount of voltage we have that's too much, 22.8, we divide it by that current, and we come up with 2,280 ohms. Well, you're not going to find a 2,280 ohm resistor. The resistors typically only have 1 or 2 digits on them. So what you will find is a 2,200 ohm. And if we plug it into the math and take the voltage and we divide it by that, we come out with a current of basically 10.3 milliamps. Close enough. It's not going to hurt anything. So 2,200 ohms is going to work just fine. Now, 2,200 ohms is called a 2.2 k ohm or 2.2 kilo ohm resistor. All right. So what do we look for in our little junk drawer? Well, if you go down to the resistor color codes, which go 0 through 9, and they go black, brown, red, orange, yellow, green, blue, violet, gray, and white. Yes, I've been doing this for a while. Number 2 is red. So the first digit is a 2. The second digit is a 2. And the last bar basically tells us how many zeros to add, which is 2. So 3 red bars. Dig through our little box and we find that. We can put it in, and when we do, what will happen is when the output port goes low, the voltage will go from our 24 volts through the resistor into pin 1, drop through the LED to pin 2, and out through the output port. The LED will light up, the phototransistor will conduct voltage, and 3.3 volts will go through our device in pin 5 through the photodetector and out pin 4 to ground. Sounds like a Rube Goldberg, but that's how it works. Now, the Arduino pin. All right, so we're going to leave our 24 volts and our output port and all that side of it exactly the same. No change whatsoever. We still have our 3.3 volt signal. Now, if we're connecting up an Arduino, normally you would connect that 3.3 volts to the Arduino pin, and that's what would cause it to detect a signal. We're going to do something similar. We're going to take the 3.3 volts, put it to pin 5, and when 5 conducts, that voltage will be available on pin 4. So we make our connection, we connect our Arduino input port, and then when we put our output port on our Mesa card, the LED lights up, the photodetector does its thing, and the Arduino input gets a 3.3 volt signal and activates. Incidentally, pins 1, 2, and 3 will not be physically connected to pins 5, 6, and 4, so you don't ever have to worry about that 24 volts jumping over and getting into your stuff on the right. In fact, this particular chip probably has a 600 or 1,000 volt arc tolerance on it, so unless you're doing some crazy high voltage, which would burn it out anyway, you're not going to have an issue. Great device to use for isolation. It's one of my favorite devices. So let's go to the lab. Oh, yes, one more thing. Need to connect the Arduino port to ground because, you know, it's going to have its 3.5 volts on ground, and I didn't mention that. So we connect that up. Just want to make sure you got that. Now let's go to the lab. All right, we're back at the lab. So I'm going to disconnect the stuff that we don't need and just make it a little bit easier to work on here. So we have our output here with the 24 volts, and we want to take this 24 volts and we want to put it into this first pin, but we don't want to blow anything out. And as we saw, we need a 2.2 kilo ohm resistor. I've got these laying around, may as well use them. So we will take a 2.2 kilo ohm resistor and connect it up like that. So 24 volts now will come out here. Actually, nope, sorry, wait. I'm forgetting my own lab. We got to go here to supply the ground, and then we supply 24 volts to the input through the resistor. So we'll connect this up. So now when this goes low, it will allow the 24 volts to go here through the resistor and back out into this. So this side is all set up now. So now what we need to do is we need to just set up an LED or something to act as our output driven device. So I've got an LED right here, and I can set it down like this. Let's see, that's the positive side. So I can go like this. Then I can tap 5 volts from here into the optocoupler there. Then I can take the output of the optocoupler, connect it to the input. Let's move this up here so you can see it better. To the input of the LED, like that. And I need a resistor for here, and I know that an LED like this uses about a 200 ohm-ish, 150 to 200 ohm resistor, and I've got some of these laying around. So I'm going to take it and stick it in there, and I'm going to connect that up to the ground. So now if I apply a signal to this, it should turn on, provide the ground for here, and it should turn the LED on. So let's find out. So let me hit the control, and how about that? It works. So we've got a 24 volt signal driving the 5 volt LED. And if I had a 3.5 set up, I could do it with 3.5 to just be a slightly different resistor. But this proves it, and the lab shows it works. Yay! This video is kind of long. I think I'll stop now, and if there's an interest, I'll make another video showing the connection for an input using the opto-isolator. If you want that, let me know in the comments below. Thanks.